Hi, I'm Matt Gordon, and this is Getting Started with Micrium OS. Up until now, we've considered interrupts mainly at a high level, but today we'll get into the details of how Micrium OS handles interrupts. As we saw in our last video, the topics of preemptive scheduling and interrupts are closely related. It's through interrupts that a new task can become ready to run without any action from the currently executing task. Before we get any further, let's review some important definitions. An interrupt is a signal that informs the processor of an event that needs immediate attention. For example, the completion of an A to D conversion, or the reception of a byte of data through a UART. The signal forces the execution of code that is located at a specified address. The details of interrupts vary slightly according to CPU architecture. But generically, we can refer to the code that runs immediately following one of these events as an interrupt handler. This code is also known as an interrupt service routine, or ISR. Most embedded developers are familiar with interrupt handlers, as they are a common presence in the foreground-background systems we discussed in earlier episodes. But now, let's examine the unique requirements that kernels place on interrupt handlers. This snippet of pseudocode lists the operations required for interrupt handling in a Micrium OS-based system. It's important to remember that you are not responsible for implementing everything seen here. As we'll discuss later, many of these operations are performed by the kernel, but we're reviewing them all to get a complete picture of interrupt processing. The first step in responding to an interrupt is to save CPU registers. The idea is to ensure that any values loaded into the registers are not overwritten and lost by the interrupt handler. On many CPUs, including the Cortex-M cores at the heart of Silicon Labs microcontrollers, some CPU registers are saved automatically by hardware. The particulars of saving registers differs between foreground-background systems and kernel-based applications. This is because a handler in a kernel-based application does not always return to the task it interrupted. In other words, kernel-based handlers save registers not only to prevent the interrupted code's values from being overwritten, but to prepare for the possibility of some other task gaining control of the CPU. In Micrium OS, the second step of responding to an interrupt is to call a kernel routine named OS_int_enter. This function increments a counter that tracks the level of interrupt nesting. How does the counter do this? Well, when an interrupt occurs during task execution, this counter is simply incremented to a value of 1. But when interrupts nest, resulting in handlers that interrupt other handlers, larger values are possible. Through the counter, the Micrium OS kernel has a convenient processor-independent mechanism for checking whether or not an interrupt handler is being executed. This is important because there are many kernel operations that cannot be performed inside an interrupt handler. For example, interrupt code is not allowed to create a task or wait on a message to be placed in a queue. The call to OS_int_enter helps the kernel enforce these restrictions. The function call shown after OS_int_enter should be provided by application code. In fact, it's the only portion of the interrupt handling operation that is left to your application. As you can see here, we've labeled the function appISR. So what should appISR actually do? The short answer is that it should attend to the source of the interrupt. Typically, that source is a peripheral device. In this example version of appISR, we have two comments indicating that the function first clears an interrupt flag and then signals a task. Signaling a task would be accomplished with the kernel function. This is one way for the interrupt handler to bring about a task change. However, there's no requirement for interrupt handlers to directly influence task execution. And it's also not necessary for the interrupt handler to involve any kernel functions beyond those expressly called out here. What happens in appISR is mostly up to you. Following appISR, one of two things can happen. The first possibility is a simple return to the interrupted task. In other words, a return to the code that was running before the interrupt that triggered appISR. The return would involve restoring the register values that were saved at the start of the interrupt response. The second possibility is a switch to a higher priority task enabled by the code in appISR. In this case, register values corresponding to the new task would need to be restored. Let's look at how all of this happens. Following appISR, we see a call to the function OS_int_exit. This kernel routine decrements the same counter that OS_int_enter increments, and it also runs the Micrium OS scheduler. The implication is that OS_int_exit makes the decision as to whether or not the interrupt handler should conclude by switching to a new task. There's a proper name for the process of switching to a new task or passing CPU control from one task to another. It's called a context switch. And what we've covered here could be considered a context switch initiated by an interrupt. In an application based on Micrium OS, it's also possible for tasks to initiate a context switch. For developers who are getting started with the kernel, the details of a context switch are not incredibly important. However, it's certainly helpful to understand the kernel services and function calls that lead to these changes in task execution. The series of operations that we've discussed thus far apply to more than just application interrupt handlers. In most systems based on Micrium OS, the kernel has a handler of its own that follows the same steps. The handler is for periodic tick interrupts generated by a timer or a similar peripheral, and it can serve as a template for your own interrupt handlers. Of course, the kernel's tick handler is used for more than just a template. The handler's real job is to help the kernel implement a number of time-related services. The tick interrupt typically executes at a rate between 60 Hz and 1 kHz, but it can take on any frequency that a system's underlying hardware is capable of supporting. It allows the kernel to implement time delays, software timers, and timeouts for pending or blocking functions. We'll be discussing functions of this type in an upcoming video. Time delays are a commonly used tick-based service, and Micrium OS provides a couple of functions for creating delays. The first of these functions is named simply OS time delay. It accepts a delay specified as a tick count. This can be an absolute value, which the Micrium OS internal tick counter must reach before the calling task is made ready to run, or it can be a relative count, referring to the number of ticks from the current counter value until the task is made ready. The second function is OS time delay HMSM. In this function, the delay is specified in the units represented by the last 4 letters of the function's name: H for hours, M for minutes, S for seconds, and another M for milliseconds. Units aside, the implementation of the two functions is similar. The decision of which function to use in your application code mostly depends on whether you would prefer to convert the HMSM units to ticks yourself or allow the kernel to make the conversion. So, to sum up what we covered today, when an interrupt occurs, an interrupt handler takes charge. The handler must make calls to the kernel functions osint_enter and osint_exit. It must also save and restore CPU registers. However, these operations do not need to be implemented by you, the application developer. You're responsible only for the code that deals with the source of each interrupt. After an interrupt has been serviced, the flow of execution might return to a previously running task. Or the Micrium OS scheduler may execute another higher priority task. And finally, there is one handler that is built into most systems based on Micrium OS, the kernel's tick handler. This handler is behind a number of different kernel services, including time delays. In our next video, we'll look beyond basic task management to other kernel services, starting with synchronization. See you next time.